welcome back. In the last few videos, we have discussed quite a few things about binomial random variables. We know how to check whether a random variable is binomial by using Bernoulli trials, and it's when we want to know how many successes that there are in a certain number of Bernoulli trials. That's what a binomial random variable measures. We know how to write out the binomial model with its parameters n and p, the number of trials and the probability of success, and we know how to calculate all different kinds of binomial probabilities. So the probability that the number of successes is equal to a number, less than or equal to a number, greater than or equal to a number. We saw the cereal box athlete examples. We used the pop quiz example. So hopefully you're pretty comfortable with those. Let's talk about a different example. Here we go. So people with type O negative blood are called universal donors because their blood can be donated to anyone. No matter what blood type someone is, their body will accept type O negative blood. However, only 6% of people have this blood type. So let's say there's a blood drive and a lot of people show up to donate blood at this blood drive. What is the probability that the first O negative donor is the 10th person in line? So, again, we're being asked for a probability here, so we need to use some kind of model, some kind of distribution. We've only heard of two so far. The normal distribution, or the normal model, is only for continuous random variables. And this one is not continuous. It's discrete because the donor can either be the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, or 10th person. Okay? So we can't use the normal model here. What about binomial? What did we say a binomial random variable measured? How many successes there are in a certain number of trials. Is that what the random variable in this question is measuring? Well, we need to know what the random variable is first. So what is x equal to here? Well, you can already tell this is a little different, right? The random variable here is how many people, how many donors it takes to get that first person that's O negative. This is the random variable because we don't know where this first O negative donor is. It could be the first person, it could be the fourth person. We want it to be the 10th person, but it could be the 50th person, right? That is the thing that is random here. Where is that person in line? So this is not a binomial random variable because this is not the same thing as asking what's the probability that there is exactly one O negative donor in the first 10 people. It's specifying that O negative donor has to be exactly the 10th person. So we need 9 failures and then a success. So this is not binomial. But the model that it is, we also need to check and make sure that these are Bernoulli trials. Do we have Bernoulli trials here? Now, a trial in particular, this is the most basic component of what it is we're looking at here, is going to be whether an individual person is an O negative donor or not. So what are our conditions? What do we need to check? There are 3 of them. Let's see. One of them is 2 outcomes. We need 2 possible outcomes. Can we say that we have either a success or a failure for each person in line? Yes. A success would be if that person is O negative. And a failure is if they're not. Okay. One of the most common mistakes when people check this condition is they think about what the variable is about, blood type. And they're like, well, there are more than 2 blood types, right? So there are more than 2 possible outcomes. We don't have Bernoulli trials. This is the same idea as in the cereal box example. We had 3 athletes, but that didn't mean there were 3 possible outcomes because you're only ever interested in whether it was a HALOP or not a HALOP. For the pop quiz example, each of the questions could have been A through E, but it didn't matter what the actual letter was. It only mattered whether you got the question right or wrong. So it depends on how the question is being asked, right? It depends on what the random variable represents. Yes, there are more than 2 blood types, but for each person in line, either that is an O negative person or it's not. I don't care if they're type A or AB, or I don't even know what all the blood types are. And as a statistician, that's not my job. All I need to know is, are they O negative or not? So this condition is met. Another one, is the probability of success the same for each trial? It's going to be hard to check this condition if you don't check this one first and define what it means to be a success. If a success is someone that has O negative blood, what's the probability that a random person has O negative blood? 6%. Is that the same for every person in line? Yeah. We don't have any reason not to believe that. I mean, I guess if we were like medical professionals that studied blood types, we could say these type of people are more likely to have type O negative blood than these people over here. But, there's nothing in this problem that would suggest that this is not the case. So the probability of O negative blood is equal to 0.06 for each person. So we meet that condition as well. Third condition, and this is the last one. We need every trial's outcome to be independent of all others. Again, the only outcome that we're interested in here is whether someone has O negative blood or not. So is it reasonable to assume that one person in line's blood type is independent from everyone else's blood type? Maybe. So the best I can say here is that this is a reasonable thing to suggest. Again, I'm not an expert. I'm not a medical professional. Is blood type hereditary? I really don't know. So maybe it's a problem. Maybe this condition is not met because if blood types are hereditary, like if your mom is O negative and your dad is O negative, and you are O negative, and you're all in line at this blood drive, this condition is probably not met because blood types are hereditary, potentially. I don't even know, right? So this could be a problem. And if this condition isn't met, we're not going to be able to use the model that we need to answer this question. Luckily, there's a workaround for independence among individuals. And that is, if your population is big enough and you're only sampling a very small proportion, then the probabilities can be assumed to be independent. So let me try and give an example of this. So when you draw from a standard deck of 52 cards, the probability that the first card you draw is a spade is 13 in 52, or 1 in 4, right? Let's say you take that card and you're sampling without replacement. So you put the card off to the side and you draw a second card. Say that card was a spade. The probability the next card is a spade is 12 out of 51, right? That probability has changed. The probability of getting it the second time is different than the first time because it depends on that. It's a conditional probability. Now, instead of a deck of 52 cards, let's say you're drawing from a deck of 10,000 cards. Right? You can imagine this deck of cards is on a table, and the cards go up to the sky. I don't know how tall that would be. But anyway, let's say you draw from a deck of 10,000 cards. The probability that you draw a spade, let's say it's still 1/4, right? So from this giant Jenga tower of playing cards, you somehow take a random card without everything falling over. You put it over here. The probability that the next card is a spade, given that the first one was, is still going to be really close to 1 in 4, right? The bigger your population is, the less the population changes every time you sample one. So, if you are sampling a small enough number from a large enough population, yes, technically, if you're sampling without replacement, those probabilities are changing each time, but they're changing by so little that we're saying it doesn't really matter. So what I'm trying to say here is, as long as you're sampling, this is the cutoff point, you need to be able to sample less than 10% of a population, right? So if you've got a very large population and you are sampling less than 10% of that population, then those probabilities, even if you sample without replacement, are not going to be changing very much, and you can actually consider individual trials to be independent, as long as you're sampling a small fraction of the population, less than 10%, right? So let's say you're going back to a small deck of cards. Say there are only 10 cards in the deck, and 5 of them are spades. You take the first one out, it's a spade, right? That had a 50% chance of happening. The one you took was a spade, and you take it off to the side. The probability the next one is a spade is actually just 4 in 9. That probability changed from 50% to like 44%, 45%, right? It changed a lot. But with a very big population of cards, the probabilities don't change very much. So the cutoff is, as long as you're sampling less than 10% of the population, you can consider individual trials to be independent, even if you have reason to believe they might not be, right? So we might have some questions about whether family members have the same blood type. But as long as we're sampling less than 10% of the population, we're good. So there's actually a name for this idea. Okay, so here it is. Being able to consider trials independent as long as less than 10% of the population is sampled is what's called the 10% condition. So, if you are checking for Bernoulli trials, if you're checking these conditions here, and you are afraid that your trials may not be independent, whether because of the nature of the individuals themselves or because you're sampling without replacement, you have to meet the 10% condition in order to check this off and be able to use the model that you're interested in, which we'll get to in just a second. Okay? So if you're sampling without replacement or you have other reason to suggest that the trials are not independent of each other, you need to meet the 10% condition. You need to know that you're sampling less than 10% of the population. Now, we are only sampling 10 people for this question. Is that less than 10% of the population? Well, we have to know who the population is. I suppose the population is all people, or maybe all people within driving distance of wherever this blood drive is taking place. As long as we can reasonably assume that there are at least 100 people that could have been at that blood drive, then we are sampling less than 10% of the population. The 10% condition is met, and that allows us to say, yes, we have Bernoulli trials here. And even though this is not a binomial random variable, because it's not saying we need this many number of successes in this many trials, there is another model that uses Bernoulli trials. All right, this is very exciting. We're learning a new model here. So given Bernoulli trials, a geometric random variable, x, so that variable there is a geometric random variable. And in general, geometric random variables give the number of trials needed for the first success to occur. Okay, so Bernoulli trials, we knew that we needed to check for these for a binomial random variable. That is, how many successes in how many trials. Geometric is much more specific. You can only use geometric random variables if you're wondering how many trials it takes for the first success to occur. It's a much more narrow set of conditions that you're looking for, right? So we now know 3 models. The normal model is for continuous numeric random variables, and Bernoulli trials are necessary for binomial and now geometric. Okay, and these are both for discrete quantitative variables, right? So let's see once again, now that we are aware of a new model, let's see if we can derive how the probability formula works. That way you'll understand it instead of just being plugging stuff in and not knowing what you're doing. So to figure this out, let's take it piece by piece, right? We need the first O negative donor to be the 10th person in line. So what needs to happen? The first person needs to be not O negative, right? The second person needs to be not O negative. The third, not O negative. The fourth, the fifth, sixth, seventh, eighth, and ninth. We need each of the first 9 donors to be not O negative. Let's find the probability of that happening first. So we are looking for this first. Now, it might be easiest to split it up into individual people, right? So we need the first, second, third, fourth, fifth, sixth, seventh, eighth, and ninth people to all be not O negative. And because we have assumed that each person's blood type is independent of all the rest because we met the 10% condition, if we need the first and second and third all the way up to and ninth being not O negative, we should just be able to take each person's individual probability of being O negative, so we'll have 9 of them, and do what with all those individual probabilities? And means multiply. And since they're independent, it's that easy. So all we're doing is taking the probability of being not O negative, which I'm using the notation of a complement here to denote that, and multiplying it by itself 9 times. So this is going to be whatever the probability is of a person being not O negative raised to the 9th power. What is the probability someone's not O negative? Well, the probability someone is O negative is 6%. So the probability that they're not should be 1 minus 6%, which would be 94%. So this is just 0.94 to the 9th power. And you may be aware before you plug that into a calculator, if you take a number less than 1 and raise it to a power, it's going to keep getting smaller. And it turns out 0.94 to the 9th power is, I don't know what that is yet, and we'll deal with that in just a bit, because this is not really the answer to this question yet, right? For this to happen, we need the first 9 people to be not O negative and the 10th person to be O negative. So what is the probability that the 10th person is O negative? Well, does it make any difference that that person is 10th in line? No, it doesn't matter where they are in the line. Each person is independent. So this might as well be asking, what's the probability that a random person is O negative? 6%. Right? So, in order for the first O negative donor to be the 10th person in line, the first 9 people are not, and the 10th person is. And means multiply. So, the probability, and I could write this out in words like I have here, but we've already defined the random variable x to be the number of donors until the first O negative donor. So what we're trying to find here is the probability that x is equal to 10, right? That it takes 10 people until you get the first O negative donor. And that's going to be equal to, we need this and this to happen, and these events are independent. So we multiply these two things together. 0.0344. So, again, let's get those interpretation skills fired up. How do we interpret this number here? What does it mean? It means there's a 3.44% chance that the first O negative donor is the 10th person in line. So here's our interpretation. The probability that the first O negative donor is the 10th person in line is 3.44%. Again, you can copy the exact language that's here and just tack on the value you calculated at the end, and you can put 0.0344 there You don't have to turn it into a percentage if that's something that has always been a sticking point for you ever since you first learned about the relationship between decimals and percentages. Either way is fine. So, we now have an example of how to calculate a geometric probability for a geometric random variable. A geometric probability is always asking for how many trials does it take, how many Bernoulli trials, until the first success. And so we saw here that all we have to do is take the probability of failure raised to the power of how many failures there are, because we're multiplying those together, times the probability of getting one success. That's all we did here. And that's as simple as it is, really. So if we want to generalize the probability model for geometric random variables, we can do it this way. Okay, so I moved our definition of a geometric random variable over here, and now we have this. This is what we've already figured out. The geometric model probability, so this is the geometric model. So the probability that the first success in repeated Bernoulli trials with probability of success P occurs on trial X is given by this formula here. So the probability that the random variable is equal to a particular number of trials, like 10, is equal to the probability of failure, which is 1 minus P, which here was 0.94, because the probability of success was 0.06. So that was 1 minus 0.06, raised to the x minus 1 power, right? So if we want the first success to be on trial 10, then that means we have 10 minus 1, or 9 failures, right? And then you need your success to happen last. And since there's only one success, the probability that a random trial is a success is P, 0.06, right? That's the entire model. It's much simpler than the binomial probability model. Remember, that was like n choose x, and then it had all that stuff afterwards. The geometric model is much simpler. However, it's only for a very narrow set of questions. How many trials until the first success? Or what's the probability that the first success is on trial X? That's really the only context in which it makes sense to use the geometric model. But if that is what you're looking at, it's a very easy model to understand and to use. You don't even need to remember this formula. You might be able to come up with it on your own. So to conclude this video, where we have introduced a situation in which we have a new model, the geometric probability model. We know that we need to check Bernoulli trials, right? You can't use the geometric model unless you got Bernoulli trials, just like for a binomial model. And we now know what the probability model looks like. Let's find the mean and standard deviation for a geometric random variable, right? We did the same thing for binomial. We said that the mean was n times p, and the standard deviation was, I don't remember off the top of my head. I'm not even going to guess, because if I say it wrong, I'm going to get skewered. So we know what the mean and standard deviation of a binomial random variable is. Let's find the same thing for a geometric one. So we need to find the mean for a geometric random variable. So let's forget about this example for a second. And let's say, okay, you're flipping a fair coin. The probability of heads is 0.5. How many times would you expect to have to flip that coin to get heads for the first time, on average, if it's 50-50? Twice? Yes. For something that has a probability of success of 50%, the mean number of trials to get that first success is 2. Okay, let's say I've got a 10% chance of making a half-court shot in basketball. That's probably way higher than it really is, let's be clear. But let's say I've got a 10% chance of making that shot. And all trials are independent of each other. Okay? How many times would you expect me to have to shoot a half-court shot before one went in, on average? If it's a 10% chance. 10 times. Maybe that makes sense, maybe it doesn't. The mean of a geometric random variable is 1 over p. If p is 0.5, then this is 1 over 0.5, which is 2. If the probability of success is 0.1, then 1 divided by 0.1 is 10. Okay? So it's actually really neat, I think, how that works. So for this example, p, the probability that somebody had O negative blood, was 0.06. So the mean of our random variable here was 1 over 0.06, which is 16.67. So what I'm saying is the mean of the random variable for this setup is 16.67. What is the interpretation of that value? What does it mean? It means that if 6% of people have type O negative blood, then you would expect to see the first person have O negative blood approximately 16.67 people into the line on average. Right? So if you had lots of different lines of 10 or lots of different lines of people at a blood drive, sometimes the very first person in line would have O negative blood. Other times you might have to go to the 5th person, or the 10th person, or the 20th person, or the 50th person, right? It's not particularly likely that someone has O negative blood. You might have to go for a while. But on average, you're going to have to go 16.67 people into the line before you get the first O negative person. That is how you interpret the mean of a geometric random variable. Let's also find the standard deviation here. I'm just going to go ahead and give you the formula. I'm going to cheat this time. The standard deviation of a geometric random variable x is the square root of 1 minus p over p. Why is it that? I'm glad you asked. Your textbook actually has the derivation of this formula, and it's one of the most beautiful things I've ever seen. It's really freaking cool, right? So if you're curious as to why this is, if that's why you get up in the morning to see cool math stuff, take a look in the textbook in chapter 16. You'll see how that works. It's awesome. But if you're not interested particularly, you can just plug that formula in. I believe, and I'm going to check right here, I want to know if these formulas are on the AP test formula sheet, and they are. You do not need to memorize these. You also don't need to memorize it for a binomial random variable. Here's the AP formula sheet for the test. Oop, let me see if I can focus on this here. There we go. So you can see here, for x being a binomial random variable, everything's backwards. If x is a binomial random variable, it gives you the probability distribution, the mean, and the standard deviation. And it does the same thing for geometric. So you've got your probability distribution, the mean, and the standard deviation for both of those. And you can have this on the test. So that's pretty cool. Don't need to memorize it. And so the standard deviation for our example here would be the square root of 1 minus 0.06 over 0.06, which is 16.16. Interesting. There's sixes everywhere here. Okay. And the reason the standard deviation is so large is likely because the probability of success is so small. There's a lot of variability how many people you need to look at before getting the first success here. The closer this is to 0 or 1, the bigger the standard deviation is going to be. All right. So, I think that's good. We learned a lot today. We introduced an entirely new distribution, a new model, the geometric model. You know how to check to see if a random variable is geometric. You need Bernoulli trials, you still need to check those conditions. We learned about the 10% condition, just in case you're worried that your trials aren't independent of each other. We know that the geometric random variable is the number of trials until the first success, right? And we've calculated the probabilities for geometric random variables and means and standard deviations. Now, for binomial random variables, we made a whole big deal out of whether you have the probability that x is equal to a number, less than or equal to, less than, greater than or equal to, greater than. For geometric, I would say the overwhelming likelihood is that you will be asked that the probability that you have exactly 10 trials until your first success, that this would be an equals sign. It is possible that that is not the case. We might get into it. Yes, we are going to get into that in the next video. We're going to see another example of a geometric random variable. We're going to calculate some more probabilities. You do not need to calculate this by hand, just like we did for binomial. We might be able to use the calculator for some of those things. So it's not particularly difficult to calculate geometric probabilities by hand, but you will have other options. So that'll be in the next video, which will be the last one for this chapter and for this unit. So you've got your progress checks, multiple choice part C, and the free response. Those are going to be due pretty soon. Make sure you look on Canvas for the due dates on that. Make sure you get those in. The Chapter 16 homework will also be due soon. But I can tell you right now, tomorrow's video is going to be very short. Just one example similar to this one, and I'm going to go through it a lot quicker. So it'll be a short video, and you can use any other time you've got scheduled to work on the Chapter 16 homework and the progress checks before your unit test. So you've got a lot to work through. Hopefully you can find some time to get that done. If you've got questions, let me know. Other than that, we'll see you next time.